YouTube. In this video, we're going to continue our exploration of exponential functions, but specifically those that we concern ourselves with when we talk about compounding interest. Okay, so when we talk about money accounts, we often talk about, they accrue interest at a certain rate, which would be some percentage of the original amount over time. Okay, but here's the deal: we have two formulas for compounding interest. We have this first one here for n compoundings per year. We say the amount A that I have is equal to the principal amount. Now this capital P stands for the amount that I start with. So we say A. A is the amount that is in the account. P is the principal amount. And that's kind of like saying the initial amount. Okay. We say is the principal times the quantity 1 plus R over N, where R is the rate. Okay. Now this is a percentage, but written as a decimal. This is important. If you don't write your percentage as a decimal, you're going to be way wrong as a decimal. So you want to make this note when you are doing these things, not to forget that. And then we say T is time. This is important to note. The time is always written in years, no matter what number of years. If it's 1.5 years, you got to write 1.5 years. Okay. And then we say, last but not least, N is the number of compoundings per year. Okay, so you'll notice that I wrote a little note in our little box over here, but we say use the following values of n if compounded over these times. But we say like annually, how many times a year would that compound? It just means once a year. So we say n is equal to 1 time per year if it compounds annually. Quarterly is 4 times a year, so it's like every 3 months. We say 4 times a year. Monthly, of course, there are 12 months in a year, so n would be equal to 12 if we're compounding once a month for an entire year. Semi-annually, this just means every half a year. So that's like every 6 months. However, that's twice a year. And then bi-monthly, which means every 2 months. 12 months in a year. So we'd say number of times a year would be 6. Last two here, not that they're very difficult to think about, but weekly is 52 times a year, and then biannually. Okay, this is biannually means once every 2 years. So if it's one whole time every 2 years that we compound some interest on the amount that we've got, then that's only a half a time per year, which is an odd thing to say because you would think number of times per year is discrete, but it can be a continuous number. So we say for n compoundings per year, we use this first formula up here. My second favorite formula is this guy right here. We say A equals PERT, or PERT. Okay, but this is for continuously compounding things. You'll notice that this formula right here lacks any n, because what we're saying is it's compounding interest every second of every day, every second of every second, like every fraction of a second. It is continuously growing and compounding. So for this formula, we still need the time. It is in years. We say the rate is still a percentage written as a decimal, and P does stand for the principal amount. We can solve for the amount that is in there now, given these things. And then, of course, E is our natural exponential base of 2.718-ish. So we're going to go ahead and run through an example real quickly, what this would look like in practical use. So we say on the day of a child's birth, let's assume that $25,000 is made in a trust fund or deposited in a trust fund that pays 8.25% interest. Determine the balance or the amount A on this account on the child's 26th birthday if the interest is compounded these ways. Okay, so let's start with this. First of all, we want to write down what we know. So the principal amount we've been given is $25,000. That is what we're starting with. It seems we have a rate of 8.25%. However, we need to take this decimal and you just simply slide it twice to the left. That's how you convert from a decimal or percentage to a decimal. So this would be 0.0825. I get this question a lot. Do I have to write the 0 before the decimal? No, you can write this as 0.0825 if you think your eyeballs won't miss this. However, it's just good practice to put the 0 out front. So that's our rate. And then we say determine the balance in this account on the child's 26th birthday. So we'd say this would have been going on for 26 years. Okay, so let's start with this quarterly. Since this is quarterly, it's like a certain amount of times per year that we're compounding interest. We're going to use the first of the two formulas. So writing this out, we say the amount in the account after 26 years would be equal to the initial amount, which is just this 25,000, times 1 plus. Now, we need to plug in our rate. Our rate is 0.0825 over 4, because it was compounded quarterly, which is 4 times per year, to the power of 4 times the time. In this case, 4 times 26. So now, we'll just pull out our calculator. I'll slide this over here. We're going to have to be nimble how we calculate this here. We say 25, let's multiply the 25,000 last. let's just do this first. In parentheses, order of operations here, we say 1 plus another set of parentheses, 0.0825 divided by 4, end parenthesis, to the power of 4 times 26. I wonder if it'll allow me to do this. Oh, shucks. We'll try this again. I apologize. We say in parentheses here, we've got, how about this? 1 plus another set of parentheses, 0.0825 divided by 4, end parenthesis. Okay, so that's what we have there. And this is to the power of, in parentheses, 4 times 26, end parentheses. Okay, so this is this middle part to the power of this. We'll take this now times 25,000. If I had a better calculator, it'd be a little bit easier to type in. But what this would mean is after this amount of time, we'd have about $208,941. So $208,941 if I calculated this correctly. Okay, so you might say, well, that's a lot of money. Well, I'm telling you, if you let this compound over a course of 26 years at an 8.25% rate, if anybody's going to give you that, yeah, it actually would grow this tall. So let's try the monthly. How does this change if we do it monthly? So we say the amount, we still have an initial amount of 25 grand. This is 1 plus. We still have the 8.25% rate, or 0.0825. But this time we're dividing by 12. But you'll notice we're also taking this to the power of nt, where it's 12 times 26. So getting my calculator back out here, one would think, well, if it happens every month, it'd be a little bit more, or maybe a lot more. Let's find out. So we'll do what's in the parentheses first. 1 plus another set of parentheses. We've got 0.0825 divided by 12, and that set of parentheses, and that set of parentheses. Now this is to the power of, in parentheses, 12 times 26, end parenthesis, equals, and then we'll take this times 25 grand. So about 211,989. So 211,989-ish dollars. So it is more, but it was compounding interest more often. Okay, so this is how you use the n compoundings per year. Let's do one where we talk about continuously compounded interest. It's a lot easier to work with. We say, we say the amount that I have is equal to my principal amount, P. So $25,000 times e to the rate times time. So we say 0.0825 times, in parentheses, now we say 26 years. So putting this into the calculator, we'll get this out one last time. All we have to do is type this in to find the amount. But we necessarily end up with this. Let me find my E button. So we say E is 2.718, you notice here, to the power of, in parentheses, 0.0825 times 26, end parentheses, and that comes out to be this. We'll take that times 25 grand. So if I compound this continuously, I should have about 213,551. So 213,551-ish dollars after 26 years. So all three of these instances, see if somebody will give you a continuously compounded thing. So you can stop the video at this point. What I'm going to do though is I'm going to go ahead and take a look at this over the course of time in GeoGebra. What if I were to actually graph this? So we're going to go ahead and type in the function down here. And you can watch me do this. We say f of x, or our amount, let's call it a of x then, because it is an amount, and take my caps lock off there, was equal to our principal amount, which was 25,000, times, in parentheses, now we had 1 plus another set of parentheses in which we were dividing two things. We'll do the quarterly. So we said r over t 0.0825, and this was over n, so r over n, so r over 4 if we're doing this quarterly, and all of this to the power of 4 times time. So I'm going to leave time variable in this instance. We say over time x. And so I graph this. There's a reason why we can't see it right now. Is because our principal amount at time 0 would have been clear up here at 25,000. So what we'll do is we'll change our viewing options here. We'll say our x minimum, how about we start at -5 years, and we'll go out to 30 years because we were interested after 26 years. We'll go out 30 years. So change that. And then our y minimum, just so we can see the axis here, I'm going to go -5,000. Don't worry about it. And then we said after about 26 years, it was already about 200,000. Let's go up to like 500,000. If you're using a calculator, it's always good to start high and then work your way back down. So here's our money over time. I noticed that 500,000 is a little bit much, so I'm going to go 400,000. Fix it up a little bit here. Maybe even get away with going 300,000. 300,000. So we get a really good picture of this. We'll change our graphics properties just a little bit. We'll make this thicker and we'll go red. I can see red. Sorry if you're colorblind. And so here we go. You see down here on the axis, we say over time. You notice that at time 0, when we started this, we started off with an initial amount of $25,000. But after about 26 years, which is about right here, we could trace it up, and it hits my graph about right here. We could trace it over. Remember we said we'd have about $208,000-ish or something like that, which is relatively right around here. As a matter of fact, if I were to graph the line y equals 208,000, which is a constant function, it would strike my graph right over here, about 26 years, which is a very reasonable thing. But you notice that it compounds over time, but it keeps getting steeper and steeper. So if you can, put your money in an investment account that you think is worthy of your money and you think it's going to give you a good return, a solid return. But it's a good thing, because if you let your money just sit there, it just compounds on its own amount. So cheers.